The next three sections of Chapter 5, we're going to consider some alternatives to finding the Thévenin resistance, as well as handling circuits that have dependent sources, and then finish out with what the Norton equivalent looks like as it's related to the Thévenin equivalent. So in the previous introductory section of this chapter, we showed how you would go about finding the Thévenin resistance after first getting the voltage across the open circuit, which becomes the Thévenin voltage, and then using a short circuit to get the current of the short circuit, and then by division you can determine the Thévenin resistance. So when the network has no dependent sources, you can actually determine the Thévenin resistance directly by a technique called zeroing the network. In other words, that is reducing the voltage to zero for a voltage source and reducing the current and a current source to zero. So we use this technique to figure out what the resulting resistances would be. So the idea is basically to replace the voltage sources with short circuits, which would have a representation of no voltage, and replacing current sources with open circuits for which there would be no current between the terminals in that case. So the idea, as illustrated here at the bottom of page 68, is here we have the original Thévenin equivalent. Remember, the Thévenin resistance is attached here to the positive polarity of the Thévenin voltage. And the idea of zeroing out this source is just to create this short circuit there, where you'd basically remove the voltage source and replace it with a conductor end to end from those two nodes. After zeroing the sources, you could actually combine all the resistances, maybe exploiting series and parallel, and the resulting equivalent in that case, you can easily show would be the same as the Thévenin resistance. So this is a really nice technique to zero the sources and figure out what the resulting equivalent would be, and that will be the same as the Thévenin resistance. So let's try this technique out. We're going to go over to page 69 now and look at an example here where we will find the Thévenin equivalent of the circuit below. And the idea first is we're going to zero sources to actually get the Thévenin resistance. All right. So first of all, we have to recognize, well, what are our sources? In this case, we have two sources there. We have a current source of 2 amps, and we have a voltage source of 20 volts. Right. So zeroing the sources, it's either using a short circuit or an open circuit. Remember, to zero out the voltage, we would need a short circuit, so we will provide a short circuit there. We would still have the 5 ohm resistance connected to the 10 ohm resistance, the 20 ohm resistance here. And of course, we're zeroing out the current source, so that's an open circuit. So we'll just represent it that way. It's an open circuit, and then we continue on to the original terminals that we had for the original circuit, right? So the idea now is to look at how to reduce this to an equivalent, and that will be the Thévenin resistance, okay? So the idea is to think about, well, is there any relationship between series and parallel? And of course, if you realize that these are actually attached end to end, you could bend the wires around and actually show that they actually would look parallel. So in this case, they are. So 5 ohms and the 20 ohm resistances are in parallel, and we know how to compute that equivalent, right? So in this case, the equivalent, of course, is 5 times 20 over 5 plus 20, which was 100 over 25, which is 4 ohms. And that is, by definition, the Thévenin resistance, okay? After zeroing sources, that's ultimately how much resistance you have in the circuit, okay? Right? So now our goal, though, remember, is to find the Thévenin equivalent. So we've only got one piece of the puzzle. Remember, there's 3 pieces: Thévenin voltage, resistance, and then the short circuit current, okay? So we'll add the short circuit now between the open terminals, all right, and see if we can, we're going to see if we can deduce some information here, and then obtain, hopefully, use KCL as indicated here. For a top node, and see if we can figure out what the short circuit current is, right? So let's go ahead and then do the short circuit. So we will draw original 20 volt source. Let's call that V sub S, just to identify. And we have the 5 ohm resistance, and we have the 20 ohm resistance. Okay. And here's the 20 ohm resistance. And we have the current source from bottom to top. And we are creating a short circuit. Okay. All right. So when we create the short circuit, enter stage right, in this case, the short circuit current. That's what's going to happen, right? But something else happened here. When we create the short circuit, we have current, but we have no voltage, okay? So across these two, from the top node to the bottom node there. So what that means is that the voltage across the 20 ohm resistance became 0. Okay, so another way to look at it is there's these 3 items here, including this single conductor. Everything here, there's no voltage here. So anytime you connect end to end the components of a circuit element like this, right, you will nullify it out. In other words, there's 0 voltage here, there must be 0 voltage there, there's 0 voltage there, okay? So that's actually effectively you're shutting it off, okay? There's no ability to absorb any more energy there because of that short circuit, right? So the current through the 20 ohm resistance is also 0. And that's just because of Ohm's law. If the resistance is 20 and the voltage is 0, then the current's 0, all right? That's just Ohm's law. But if we were to represent currents, let's say I1 is the current through the 5 ohm resistance, and originally we had said I2 here is the current through the 20 ohm resistance, can't be the same value simply because they're not in series, because we have, or you could say this current comes in and flows outward either way, even though I'm taking the reference directions this way. Doesn't really matter which way I take them, but either way, they're representations of different currents there because they're not in series. So, but however, we've already shown that there is no current throwing through the 20 ohm resistance, so I2 is 0, right? Okay, so and keep in mind these are independent. I should put the polarities here. Keep in mind these are independent sources there, of course. But the voltage across the 5 ohm resistance is, let's see if we can deduce what that is. Well, no voltage, no voltage, no voltage. We have 20 volts on this end, right? So 20, so we have 20 volts going across this, right? Before it hit 0. So there's 20 volts going across the 5 ohm resistance directly connected to it, okay? And because of that, by Ohm's law, we know that I1 must be that source divided by 5 ohms, which is 20 volts over 5 ohms, which is 4 amps. So there is 4 amps of current, okay, going across that 5 ohm resistance. Now, if we looked at KCL, let's say top node, okay, so looking at KCL up here, this is all one node here, okay, right? So if we look at the KCL equation there, we're just simply, let's write it from the perspective of summing, let's say the outgoing, just so we understand how we're designing it. We're doing the sum of the outgoing currents and setting them equal to 0. It's one way of applying KCL, right? So this top node, summing the outgoing currents equal to 0, right? So what do we have? Well, we've represented I1 coming inbound, so that means the equation would have a minus I1 there. Then we definitely have, we've represented an outgoing I2. I'll go ahead and put it in here technically. but we know it's already equal to 0. So this is really going to be no factor, but just for the sake of the argument, it would be there, but we already know that's 0. And then this is an incoming current, and that would have to be -2. And then we have the outgoing short circuit current, ISC, and that has to be equal to 0, okay? So that should make sense. There's 1, 2, 3, 4 currents involved, although one of them we already know is 0 because there's no voltage there because of the short circuit, all right? So if we solve for ISC, okay, what would that mean? If we solve for ISC, again, we go ahead and substitute values now. We'd have -4, -2, plus ISC equals 0, or that the short circuit current really is 6 amps, okay? Right? Again, that's critical now, because now we can use our relationship that the Thévenin voltage, right, is always the product of the Thévenin resistance times the short circuit current, okay? So in this case, you'll take the 4 ohms for the Thévenin resistance and multiply it by the 6 amps and get 24 volts. So the Thévenin equivalent that we would draw for that original circuit is simply a 24 volt source, that's V sub T, connected to a 4 ohm resistance, and we'll call that R sub T, okay? Again, that's our Thévenin equivalent. And make sure that the resistance is in series here and it's connected to the positive polarity of the voltage source, all right? So rehashing. The strategy here was to get the Thévenin resistance by zeroing out the sources, then adding the short circuit so that we could deduce with KCL what the ISC, or what that short circuit current would be. And again, this 3-parameter equation, all you need is 2 of them. So in this case, we determined the right 2, the RT and ISC, and immediately you can get the Thévenin voltage, okay? It's a really, really nice technique that is very handy. But one thing to keep in mind is we're only zeroing out independent sources. So I'm gonna write that down again to make sure this is very clear. These were independent sources. Didn't depend on a parameter. It didn't have a gain parameter that's connected to a voltage or current somewhere else, all right? So that's very, very important in this technique. We're only applying it to independent sources, right? So let's move on to another example. We'll go on to page 70 and just getting some more practice here. And this time we're going to revisit the same example. The only difference is I just want us to illustrate that our answers are correct, and we'll do that by using node voltage analysis. So sometimes it's nice to just sort of go back and see if we could have gotten the result in a different way, all right? So again, this is exactly what we just did, all right, on page 69, but this time we're going to do MVA, all right? We're going to apply MVA and see if we will come up with the same result. First of all, we go back and realize that the Thévenin voltage will always be the same as the voltage across the open circuit. So if we can use MVA to determine what VOC is, then we have the voltage that way versus the way we just got it earlier was finding the other 2 parameters, right? So notice that we've done MVA and we've decided a ground. So let's go ahead and for this node V1 up here, let's draw its polarity curve, its polarity arrows there. If we come into the positive, then we're positive. If we come into the tail, we're negative in terms of doing KVL, for example, all right? So we're doing MVA, and let's think about using that top node and do a KCL equation. Again, we're just verifying the answers that we've already gotten, right? And let's do this from the perspective of the sum of the outgoing currents. If you're noticing, yes, I switched pens. The other one was kind of dying on me. So the sum of the outgoing currents is 0, all right? So let's do this. We've done this before. From the perspective of V1, if we go to the left through the 5 ohm resistance, we hit 20 volts. So that current would be V1 minus 20 over 5. Then we can go from V1 directly to the ground through 20. So that'll be V1 over 20. And then we have an incoming current right there. So that'll be a minus 2 equals 0. Because there is no current over here. We got voltage, but there's no current over there. So there's no other current to worry about. There's only 3 in this case. So let's clean this up a little bit by just taking some terms out here. So we'll get 1/5 times V1, what, minus 4, plus 1 over 20 times V1 minus 2 equals 0. Collect the the V1 terms there. So the nodal voltage there of V1 is 1/5 plus 1 over 20 times V1 equals 6 to the other side, correct? Get a common denominator. 1/5 is the same thing as what, 4 over 20. So we'll have 5 over 20 times V1 equals 6. And it won't take you long to realize the answer to that is that it's just 24 volts, right? So that nodal voltage is there's 24 volts up here, right? The ground is 0, so the differential across here must be 24 volts. So the voltage across that open circuit also must be 24 volts from being 0 at the ground and 24 up at node 1, right? So awesome. So therefore, we know that the Thévenin voltage is 24 volts, and that verifies what we just determined earlier, okay? So that just goes to show you that, you know, sometimes people may not want to zero sources and go that route. If we needed the Thévenin voltage directly, you could do it this way, okay? So there's several options sometimes. Let's move on to example 5, the bottom, page 70. Let's find the Thévenin resistance for this circuit. It's a lot more complicated, all right? And I think when you see more complicated circuits in terms of a lot of number of resistances, I think the zero source approach is probably the most straightforward, less error prone, okay? So in this case, let's look at that approach of zero sources. Okay? And again, let's check our sources. They're both independent. This is an independent current source, and this is an independent voltage source. We only zero those, right? So go ahead and zeroing them and then redrawing the circuit. So you have a short circuit coming through there where the voltage was. We have our 20 ohm resistance. Then we have a 5 ohm resistance coming down this way. So here's your 5 ohm. Here's your 20 ohm, okay? And continuing on, we have a short circuit now. Excuse me, we have an open circuit, of course, nullifying out that current, but then we have another resistance, 6 ohms here. Coming down with it over here is your 10 ohm resistance. And then the open terminals there, okay, right? So remember, when you're zeroing sources, your target there is that the Thévenin resistance is the equivalent that you will get from what's left, okay? That was the strategy, right? So now we're just going to exploit properties of the resistances, thinking about, you could also sometimes think about them in terms of, you know, what absolutely do we know has to be true? Well, if you were looking at these two on the left here being PRC, you could see very quickly they're tied end to end there. So immediately we could say that 20 ohm and 5 ohm are in parallel. And we'll get our first equivalent, because you can see you're going to get more than one equivalent. So I usually think it's easy to start at the very far end of a circuit and then work our way back over. So in this case, this means your first equivalent we'll call REQ1. They're in parallel, so that's going to be 20 times 5 over 20 plus 5, and we've seen this one over and over again. That's just 4 ohms. And maybe just to make sure we're not, you know, jumping too far ahead of ourselves, you could go ahead now and put it in. So these two in parallel simply become REQ equal 4 ohms. And then you still have the rest of the, I'm not going to draw that open circuit this time. You still have the other two, the 6 ohms, and then you have the 10 ohms, okay? right? But notice it's important here that we draw these correctly, because you can see from right to left, you have a juncture here of leaving either through 6 and 10. But once you come through, if you were heating up this resistance, 6 ohms here, and then you came PRC into that one, I would hope you'd see immediately those two are definitely in series. They're end to end in this case, okay? They're not in parallel. So our second equivalent is just reflecting the fact that REQ and the 6 ohm are in series. And so in that case, we'll reduce that equivalent, will be REQ2, would have to be the sum, right? So that'll be 4 ohms plus 6 ohms, and you would get 10 ohms. So these two would collapse into 10 ohms. So you could even write that here as 10 ohms. And then you still have this 10 ohms coming down, and that's it, right? That's all you have left. You have those two left, and I would hope you could tell me what the relationship is between those two. They are attached end to end, so 10 ohm to 10 ohm are in parallel. So finally, the last equivalent with no subscript is simply 10 times 10 over 10 plus 10, 100 over 20, and it's 5 ohms, okay? And why is that significant? That's your Thévenin resistance, okay? It's not the equivalent because you still need your voltage and your short circuit current, but still, very nice way of getting the Thévenin resistance, okay? Now let's move on, keep moving on to page 71, and let's look at the case where we actually do have dependent sources, okay? So this is finding equivalence, but now the issue is you may have independent sources, which in this case, the 10 volt in this problem here, the top of page 71 is definitely independent, but this is a dependent source, right? One way you know it's a dependent source is the diamond. Remember, the dependent sources will always be of diamond shape. You could think of that D for diamond, if that works for you. I mean, whatever you know, makes sense for you. So in this case, what we're going to do is we're going to go ahead and look at applying NVA first with the reference node at the bottom to get a KCL equation, okay? Because you can't zero that source out, okay? It's dependent, we can't zero it out, so we've got to work with it. So we're gonna label this top node, say V1. Again, there's our node 1, and we're gonna apply, node 1, and we're going to apply NVA. If we're going to do that, let's ground as far away as we can from it. So there will be our ground. And keep in mind that we have a voltage across these open terminals there, and we'll align our polarities to match that of the 10 volt. That's typically the best approach to do that, just to keep things consistent. Since we are doing NVA and we've grounded the bottom, we could draw our voltage arrow there, where polarities, representing our polarities, okay? And look at KCL then on node 1. Okay, so we're doing KCL on node 1 here, right? So again, now one thing that we've done here is, because this is a dependent current source, that gain parameter, which is has no dimension because it's current controlled, right? So this is 2 times IX, where IX actually is the current flowing through the 5 ohm resistance towards this top node V1, right? So this is, again, up here is all of our node at the top there, right? So if we're doing KCL top node, right, we could immediately say, well, let's do sum of outgoing currents is being set to equal to 0. Well, if IX is an incoming current there, then clearly outgoing from V1 must be IX, negative IX, right? And then the same logic says, well, then we have to have minus 2IX because this incoming dependent is an incoming, not an outgoing. And then we need to represent the current going through the 10 ohm resistance, right? The ground is voltage 0. There's VOC between the open terminals. So the voltage up here at node 1 has to be actually V0, right? So this has to be plus V0 over 10 and set that equal to 0, okay? So it's implicit here that V1 has to be whatever the voltage across that open circuit is, because the voltage at the ground is 0 and there's some voltage here. Well, that's the voltage at V1, okay? All right, so if we solve this out very carefully, minus 3IX plus VOC over 10 equals 0. Doesn't take long to say, well, 3 times IX is really just VOC divided by 10. And we're going to use that relationship in a second, okay? So when you have dependent sources like this, what we ultimately have to do is get that parameter that's controlling that dependent source somehow in terms of one of our Thévenin parameters. In this case, it's easy to get it in terms of VOC, because remember, this is the same as the Thévenin voltage, right? So that's the goal, is to get that dependency, somehow that dependent parameter there, somehow in terms of one of our Thévenin parameters, okay? So if we now write the controlling variable, right, in terms of it, another way, using NVA, it's just a little trick here to say, well, if you were doing NVA back up here, right, and we look strictly from a voltage standpoint, we already know the voltage here is VOC. It travels to 10 through the 5 ohm resistance. And by the way, that's by definition the current through it. Then what we would have had is that, use a pen here. Let's say this, we know this is true. We just determined this, that 3IX is related to VOC that way from our top box. But another name for IX would have to be, I'm going to be careful here, I'm going to write it as 10 minus VOC over 5. And you may say, well, why didn't you write it as VOC minus 10? Look at its direction. So from NVA standpoint, we would go from V1 through the 5 ohm resistance to 10 and write VOC minus 10 over 5. But that's not the current reference direction here, see? So we've got to flip the sign. So that's why this is written this way. And that's, and now this has to be equal to VOC of 10. And so we solve this equation right here, okay? So if we solve for that, let's just do that quickly here. Let's see what we would have. You're going to have 3 times, that's 2 minus 1/5 times VOC, has to be 1/10 VOC. So that's going to be 6 minus 3/5 times VOC, has to be 1/10 VOC. So collecting a common denominator of tenths, that's going to tell us that 6 has to be equal to 7/10 VOC, or that VOC is 60 over 7, which is about 8.57 volts, okay? And again, that's the same as the Thévenin voltage, okay? All right, okay. So we know the Thévenin voltage is 8.57 volts. And our goal, again, is to get the Thévenin equivalent. So we've got one of the 3 parameters figured out, right? Having exploited the fact that we can write this dependency here, the definition of that dependent source, we've got the parameter, in this case, that IX, cast in terms of the Thévenin voltage we're solving for, and we're able to get it. Now we'll go ahead with a short circuit and see if we can get ISC. So we'll flip over to page 72. And I will redraw the circuit now with the short circuit. So we have to go in and draw the short circuit in. So we still have the 10-volt source here, which is independent, connected to the 5 ohm resistance. And remember, the IX was the current through left to right. And this was connected to a dependency here, dependent current source, which doubles whatever the current is coming out of that 5 ohm resistance. These two things are then connected, and this is connected in parallel with the 10 ohm resistance. And then we short circuit, right? And we short circuit by connecting these together. And when we do that, we produce that current with no voltage, right? So we've seen this again. The minute you short circuit end to end, this node and this node, which these terminals, which align with the terminals of the resistance, what just happened? There's no voltage here, there's no voltage there. So that means there's no current flowing through the 10 ohm resistance. Why? Remember, the voltage equals 0 from the short circuit, okay? That's why, right? Well, so there's no current here, right? Okay. And remember from Ohm's law, if we have this current representation with 10 volts going through the 5 ohm resistance, right? We know Ohm's law over here on the left that really IX is nothing but 10 volts over 5 ohms. So we know there's 2 amps there, okay? All right. So if we look at KCL on this top node, again, all of this, and we're going to do a KCL top node there, okay? So in KCL, top node, see if we can get ISC. Well, what would we have? If we could do this in a couple of ways. Okay, there's no current here, so we could remind ourselves just here, 0, there's no current there. So one outgoing current is ISC, so we'll have ISC, okay? We also have, if we were summing outgoing currents, this is incoming, so we'll go ahead and write it as minus 2IX. And then this looks like it's incoming as well, so it means we have to subtract it as outgoing and set that equal to 0, okay? All right? So what we really have is that what the short circuit current really is, right, is whatever 3 times IX is. But we just determined it's 2 amps, so it's 3 times 2 amps, so it's 6 amps is the short circuit current. So we're there. So we've got that ISC is 6 amps. We've already determined from the other page that the Thévenin voltage is 8.57 volts. So therefore, by definition, RT has to be the Thévenin voltage divided by the current of the short circuit. So you'd have 8.57 volts divided by 6 amps, and that's about 1.43 ohms. So if we want to draw the final Thévenin equivalent for that circuit, you should draw the voltage source, 8.57V equals VT plus minus, and RT up here is 1.43 ohms, open there, okay? Awesome, right? Last thing, lecture, just to mention, sometimes we want to use an equivalent with a current source rather than a voltage source. And this is called the Norton equivalent circuit. And I want to make sure we're clear on how it relates to the to the Thévenin. They are sisters or brothers. You could look at it that way. The difference is this Thévenin equivalent is the resistance in series with a voltage source. This is the same load or the same resistance in parallel with an independent current source. But this resistance is the same as that resistance, all right? So that's very important. And the relationship is very simple, is that the IN parameter is nothing but ISC. It's the same ISC we had before, where we would short circuit the Thévenin equivalent and get the ISC value. That, in fact, is what that IN is for Norton, okay? All right? So one other thing I want to point out to you is some orientation issues here. If, for example, you had, again, just to be clear, this Norton equivalent here is matching up to this corresponding Thévenin equivalent. That's RT there. So notice positive polarity at the top, negative at the bottom, arrow points up. If for some reason you had this situation, let's draw it from this direction. Okay. Let's suppose we had this. It's flipped upside down. Okay. So here's your Thévenin resistance, plus minus, there's VT now. So this is different, right? Because now the current, in this case, the current is flowing upward. So that energy is released and absorbed. Now the current is flowing downward, release the energy, absorb, okay? So if you wanted the Norton equivalent to this, you could find the IN value, because IN is the same as ISC from the Norton, from the Thévenin, excuse me. But now you must draw the arrow down. The good thing about parallel is you can't get that wrong. There's no right or wrong on the up and down there, but it's in parallel. So notice the difference here. They need to stay in alignment, okay? This will come up very much later when we do source transformation, where at any time we can take a Norton equivalent and replace it with a Thévenin equivalent. We can take the Norton, replace with the Thévenin, take a Thévenin and replace a Norton, but you must do it in these correct orientations, right? So in summary, you can perform any of the following to the following tasks. You can determine the open circuit voltage directly, and if you can do that, you have the Thévenin voltage. From there, you can determine the short circuit by ISC value, or you could zero this independent sources and see if you could get RT directly, right? And then maybe do KCL, for example, and get ISC that way. So it's important that you write the Thévenin equivalent in the form of an independent voltage in series, and make sure that that load, that resistance, is connected to the positive polarity. You can write the Norton equivalent parallel that same Thévenin resistance in parallel, but make sure you have the current direction correct if you're coming from a matching Thévenin equivalent. But usually you can see in the circuit which way the current is flowing from the independent source, and you know which configuration you have. Do you have this as the Norton equivalent, or is this as the Norton equivalent? What was the original independent current source doing? And so we're now in a position, in the next couple of sections, we'll be using this strategy of replacing these equivalents with each other eventually when we look at source transformation.